A very good morning to one and all. I welcome back all the participants to the day 7 session 1. I take this opportunity to welcome the today's keynote speaker, Dr. Anil Kumar Garu, an associate professor in IIIT, Hyderabad, who had readily accepted our invitation in spite of his busy schedule. Thank you so much, sir. We welcome you for an interesting session on machine learning in predictive analysis. Now it's my privilege to introduce today's keynote speaker, Dr. Anil Kumar Garu. Anil Kumar Upala. Anil Kumar Upala received his BTech in Electronics and Communication Engineering from JNTU Hyderabad, India in 2005, MTech in Electronics and Communication Engineering from NIT, Kurukshetra in 2007, and PhD in Signal Processing from IIT Kharagpur in 2012. From March 2012 to June 2019, he has worked as assistant professor at IIIT Hyderabad. From July 2019 onwards, he is working as associate professor at IIIT Hyderabad. His research interests lie primarily in speech processing in mobile and practical environments. He has published 5 book chapters, 26 reputed journals, and 66 international conference papers. He is currently handling 2 sponsored projects and completed 7 funded projects. He is guiding 6 full-time PhD students. 3 of them submitted the thesis and 7 MS students. He successfully guided 2 PhD students and 2 MS students. He has given more than 50 invited talks in various workshops and conferences. Now I request Dr. Anil Kumar Garu to take over the session.
Yeah, good morning everyone. Thank you for inviting me. Can I share my screen? Is my screen visible?
Yes, sir. It's visible, sir.
Okay. Yeah, so this workshop main theme is on machine learning, right?
Yes, sir.
Yeah, so my talk goes like this. So I will give a very brief introduction about. Am I audible? These things are clear?
Yes, sir.
Okay. So I will give a brief introduction about why people are talking about deep learning, what it is actually. So why it became so popular. I will talk about some 15-20 minutes, and then I will move to how AI and ML is applied in speech processing. First of all, what is speech processing, and then what are the different techniques people are applying over the years. Okay, so. So you are seeing this machine learning or deep learning. Deep learning actually is a part of machine learning. So it is now everywhere. So already people are might be using Apple Siri or Amazon Alexa or OK Google or Microsoft Cortana, etc. applications. Or you can also see the financial predictions, healthcare domain, and social media, and across the domains. This deep learning is everywhere nowadays. Even on a lighter note, even they are trying.
Congratulations. Good. Thank you.
Can all of you please mute yourself?
Yes, sir. Okay, sir.
Okay. So, on lighter note, the deep learning is everywhere, even for predicting the election results, etc. Okay. So heavily people are using machine learning or deep learning everywhere. So we'll see what is the difference between actually what is AI, what is machine learning, what is deep learning, why people are using these many terms. So if you want to use only one term, as a common term, that should be AI. Okay, that is artificial intelligence. That means you create any sort of intelligence from the data for the machine. So that is called artificial intelligence. You can use any technique, right? So, but if you use some kind of statistical techniques, that is called machine learning. Machine learning in turn is a subpart of AI. And if you come to the deep learning is in turn, a subpart of machine learning. Um, So deep learning is basically using the deep neural networks or neural network based training. So that is a subpart of machine learning. So now why this deep learning became so popular? Why it became so popular? There are two generic reasons and two neural network specific reasons. So I this so one second. One second. Yeah, sorry. So why this became so popular? There are a couple of generic reasons and a couple of neural network based techniques. So my initial brief introduction will talk about those reasons. So so you can see in the diagram. You can see in the diagram. So earlier, actually, as such, neural networks are not new actually. So neural networks are there from 1950s, and some people will say it is a second wave, but if you closely follow the neural network evolution, so it is, we can call it as a third wave, because initially in 1950s people have introduced this neural networks. Then in 1990s also people heavily used, and early 2000s it again not so popular, but again now from last 5 6 years deep learning is the only, if you closely understand, deep learning is the one which is dominating entire AI. Okay, so the reason behind is that earlier when they proposed in 1950s or 90s, the amount of data is less. Okay, the amount of data for any problem like speech problem or image or text processing problems, the amount of data is small. Okay, so and the second thing is that we don't have a lot of computation power earlier, but from now I think you might have heard about GPU, right? Graphical processing unit. So they are expensive, but they can handle a lot of data and computations, right? So because of that, you can see in the diagram, as the amount of data increases, this deep learning started giving better results, right? So so whenever amount of data is less, even classical machine learning like Gaussian mixture models or hidden Markov models or support vector machines, those classical machine learning models may show the higher performance, but the amount of data increased, the performance increase in deep learning, that is in turn saturates for classical machine learning models. So here is the catch actually. So two reasons for generic reasons are computation power increased and amount of data increased. Computation power increased and amount of data increased. So that means we can handle the more data. That is the generic reasons. But what are the neural network neural network specific reasons why it became so popular? Why it became so popular is, you see, you may ask, sir, why once the amount of data increased, why your classical machine learning is saturating and why neural network is improving, right? So so the reason is following actually. So these basics I'm skipping, some of them might have already covered. So these are the reasons actually. So the reasons are that, you know, in neural networks, the name itself, the deep neural networks, we are calling it as a deep. So we have so many parameters. We have so many parameters to fine tune. You know, if you have more data, take more parameters and fine tune. On the other hand, if you take any classical machine learning approach, the amount of parameters in your hand are limited. Okay. For example, you take Gaussian mixture model, it has only number of mixtures we can choose, or support vector machine, or hidden Markov model. Any classical machine learning model you take, Navi base, or whatever the classical machine learning approach you take, the amount of training parameters which we can optimize are limited. That's why once the amount of data increased, also those parameters get saturated and they won't get updated much, and your performance won't improve. On the other hand, if you have more data, take more parameters which are there in neural networks. So one advantage of neural network is the number of parameters available. Okay, that if you want to say that itself, you know, you can say it as a disadvantage, but actually it is an advantage if you have more data and more computation power. It is disadvantage if you don't have more data and computation power, right? So nowadays it is not a big deal to have a more computation power and data. That's why this neural network era is going on. So what are the different parameters which we have in our hand to fine tune is number of layers, number of neurons in each layer, and that means these are the simple parameters, that how many neurons you want to use, you know, and what are the how many number of neurons in each layers you want to use, and how many number of layers you want to use actually. So if you have, or if you want to have more, if you have more data, use more number of neurons and more number of layers. And then what activation function you can use, you know. Earlier we used to use tan hyperbola or sigmoid. Nowadays people are using ReLU, softmax, etc. So you can choose the activation function to have to map the nonlinearities, right? Number of epochs. That means how many times you want to update the network, and loss functions. What sort of loss function you want to use? What is the learning rate you want to use? You want to update the weights of the neural network fastly or slowly, and also the batch size. Okay, what is the meaning of batch size? Batch size means if you have 5-class problem, that means you want to classify 5 classes. Then while training the network, we won't give first class example, all first class example, then all second class examples, all third class examples for training. We don't do like that. If you do like that, network won't be trained properly. So what we'll do is we'll take small set of data from each class and update the weights of the network, and then go to the next subset. So that is called batch. So each batch contains small number of examples from each class. Okay, so even if your network parameters are all fixed, even this batch size will batch size also change the performance actually. So we need to choose the appropriate batch size. And similarly, we have kernels, momentum parameters, number of features, etc. So what I'm trying to say here, the first point is neural network has a lot of parameters to fine tune. Okay, that is the first reason it became so popular. Second reason, the important reason, is that it is not listed here, but I'm telling orally, so you can visualize, it's easy actually. So the second reason behind why deep learning are popular, and why all of you without any choice has to use deep learning along with the classical machine learning. Let's say you want to use classical machine learning, you can use, but you have to generate results on deep learning also to compare. Obviously, if you train properly, deep learning will give better result than classical machine learning. That is proven in many cases, except very few cases where data is very less, where even transfer learning we can't use. What is the meaning of transfer learning is, already we have pre-trained network on some data, we'll use that network and try to use our less amount of data to optimize that network. So even if that is not possible, then only you may need to use classical machine learning. Otherwise, you have to use for whatever may be the problem, you have to use deep learning. Now, my statement is what I'm telling my statement, whatever may be the problem, you have to use deep learning, right? Whenever you want to do classification or regression or whatever, or any prediction, so we have to use deep learning. So why we have to use whatever may be the problem? Why we have to use that? Why it is forced to use neural network only? So how and also second and most important question is that how single model can address all problems? Earlier if you observe earlier, we have, depending on the problem, we have different approaches. For example, you take speech recognition or machine translation or video summary or video analytics. Their hidden Markov models are famous. For classification, support vector machines are famous in image processing. Similarly, Gaussian mixture models are famous in speech processing. That means depending on your task, there are different modeling approaches are available. But now my statement is that whatever may be the problem you are working, you should use deep learning. Then the question is that how it will suits for all problems. Yeah, that is the beauty of neural network. That is the second beauty of neural network. What I'm trying to emphasize is that neural networks has the concept of architecture. Okay, it has the concept of architecture. Please remember this word architecture. You might have studied computer architecture, etc. Yeah, in similar lines, neural networks has the architecture. That means simply that what is the meaning of architecture is that how your neurons are connected to each other. Okay, how your neurons are connected to each other. So we have we have a lot of we have a lot of architectures available actually. So you might have heard about convolution neural networks, recurrent neural networks, or simply you might have heard about feed forward neural network, feedback neural network, and LSTM, BiLSTM, autoencoder. These are all comes under actually this LSTM, BiLSTM, autoencoder. These comes under recurrent neural networks. Okay, so whatever earlier hidden Markov model used to do, that is called sequence to sequence mapping. That means speech to text conversion or text to one language text to other language text conversion. So these problems are not classification problems. Actually, these are classification, but actually sequence to sequence mapping problems. So for these, hidden Markov model used to be famous, but now as recurrent neural networks become popular, they have this, for example, LSTM. LSTM is the example of recurrent neural network. What is this LSTM? LSTM means long-term short-term memory. So it can capture the sequential information present in the future so that we can use it for sequence to sequence mapping. Okay, so if you want sequence to sequence mapping, use recurrent neural networks. So no, I want to do classification. Even for classification you can use recurrent neural network, or if you want you can use simple deep neural network or DNN with attention, or come up with your own architecture. That means you connect the neurons such a way that your problem gets solved. So depending on your problem, you can choose what is the appropriate architecture. So that is the beauty of a neural network. That is why whatever may be your problem, you can use the neural network as a solution. So because you can choose the appropriate architecture and apply on your problem. So now a lot of research is happening that if you see any major any popular topmost conference in any of the field of text, image, or speech processing are dominated by these neural network papers. And in that, more importantly, what they majority of the good papers are on that coming up with the new architectures, coming up with the new architecture, or coming up with the new way of training the models, or coming up with something which is related to neural network architecture, or the way it is trained, or how can we use transfer learning, or how can we train it with the large data, etc., etc. So all works revolving around this, because this became the single solution for many of the problems. So be cautious and try to learn deep learning. And we have a lot of free tools like Keras, TensorFlow, and lot of codes are available to get the confidence that how to apply these things, and then you can use it on your data, etc. So only issue with this neural networks is that you need to have good computation power. Then only you can run these experiments. So some solution, maybe you can use Google Colab, or you can purchase high computation power at the institute level, etc. Okay, so that is the brief introduction which I want to give about deep learning or importance of deep learning. Is there any questions here till here? Are there any questions?
Hello.
Okay. Yeah. So now we'll move to IA and ML in speech system. So as time is short, I will introduce the speech application, but I may not able to uh, demonstrate or talk about all the applications. We'll take one particular application like speaker recognition or language recognition, and then we'll talk about that. And if time permits, I will show some demo as well, some demos as well which we build. So this talk also goes like this. So main key things in this talk is that I will first introduce the different speech applications and a little bit of speech basics for about 10-15 minutes, and then I will talk about how different machine learning models evolved over the years in the space of speech processing, right? In speech processing, and then what people are currently working. So these are the aspects which I will touch upon. So yeah, first of all, what is speech? Okay, what is speech? So what is the need for processing it? So speech is actually our natural mode of communication, right? Whenever you want to talk to your friend or your family member, we tend to speak, right? We tend to speak and convey your message. So, but unfortunately, how you are interacting with the machine, right? You are whether it is a mobile or a computer or a laptop. So you are giving. You need to give text-based input, right? We need to give text-based input or swiping or mouse through mouse also. You can give the input. But if you see, our parents or grandparents, they may not be feel very comfortable in using those devices because they don't know how to give right inputs, and they may not be acquainted with that. So so what may be the solution? So let us say if you give iPhone to your parents, and or whatever normal phone, they know, let us say they know only green button, red button, okay, or swiping, hardly they know how to swipe the when call comes, then they can't utilize the device properly. So what is needed is that can iPhone work based on my speech, or can iPhone understand my speech and do the task for me? So that's where this Apple Siri has come, or similarly other technology, other companies also developed the technologies like OK Google, Microsoft Cortana, etc. So you can talk, you can ask. Siri, what is the weather information? Siri, call to particular thing. If you configure it well and give it to your parents, then they may speak and utilize, little bit better than the way they can use earlier. So that is the need of this speech processing. So speech is our natural mode of communication. So if you develop speech applications, then we can build. Or you can make human computer interaction as natural as possible, right? So that is the major goal of speech processing. So this is a block diagram which shows the speech production. So very briefly we'll go through that. So these three parts, first three blocks will be inside our brain. So once your brain thinks that I want to convey message, so then we'll select the language and we'll give the neuromuscular commands. Then this is actually the speech production. This is actually the speech production. That means how speech is coming out. So you can see in the first below first diagram. So your lungs will give you the required energy. That means airflow. Okay, that lungs will give you the airflow, and that will passes through something called larynx, also called voice box, right? So it has the vocal folds, and you might have heard about pitch, right? Pitch. The rate of vocal fold vibration is called pitch. The rate of vocal fold vibration is called pitch. And then this is actually this part is called this one actually excitation source. So air passing through larynx is called excitation source. That air will hit the vocal tract system, okay, or your system. This is the oral cavity and nasal cavity acts as a system. That means it acts as a resonator to generate different frequencies. So we'll put a different shapes in the mouth, in this vocal tract system to produce different sounds, different vowels, consonants, etc. Right. So that is the brief details about speech production. Okay. So it has majorly two components. One is the excitation source, other one is vocal tract system. Okay. So this excitation source, actually there are two kinds of excitation sources. One is voiced excitation and second is unvoiced excitation. Voiced excitation means these vocal folds are active and they vibrate. If they are not active, that is called unvoiced. Okay, all vowels are voiced. As simple as that. All vowels are voiced, and consonants, some consonants are voiced and some consonants are unvoiced. Some consonants are voiced and some consonants are unvoiced. So what? How can you to give the brief example of consonant and vowels? Whenever you produce the vowel, the simple thing is that they are voiced, and also your vocal tract should be open. That means your mouth should open. Then only vowel sound will come. Whether it is widely open or narrowly open, or what is the tongue position, depending on that, different vowels will come out. But your mouth should open. By closing your mouth, you can't produce vowels. On the other hand, if you come to consonants, consonant means you have to stop somewhere in the vocal tract and release. Then only consonant will come. Okay, consonant will come if you stop and release the air. Okay. For example, to easy example is pa, ba. I think all of you know these sounds, right? Pa and ba. Try to produce, all of you please try to produce pa and ba. Okay, if you see, they look like similar in production. Your lips has to close and open. Pa, ba. The difference is that actually this is same in pa and ba. This excitation. One is stop. One is this vocal tract is not active, and other cases vocal sorry, not vocal tract. So your vocal folds are active in ba, and they are not active in pa. So the pa, first sound pa is unvoiced, and ba is voiced actually. So you might have heard, right? Kachata tapa. You might have learned like this, right? Kachata tapa, gajata dava, like that. Why we have learned like that? Why can't we learn in a different sequence, other sequence? Or you might have heard about kaka gana, papa papa ma, something like that. So why we learn like that? So the reason behind is that if you go to like if you go like kachata tapa, so you can see that your constriction will start from back of your mouth to up to lips. Ka cha ta ta pa. If you see, for pa you are closing lips. For ta you are closing your system at teeth. Ta, you try to produce ta and see ta. Ta is a teeth. So ka cha ta. For ta, if you go, you see ta. Ta means your tongue will close at different other different, more than, your teeth, before your teeth, it will close. So that means depending on where you put your constriction, different consonants, sounds will come out. That's why we'll learn like ka, cha, ta, ta, pa. So that means your your constriction, what you put in vocal tract will go from back of your mouth to up to lips. So that way it will be easier for us to learn. And also, you might have heard about you, right? Some of us say, your tongue is his tongue is bulk. That's why he's not able to learn sounds quickly. The reason behind that is your tongue has to play a lot of role to put a constriction and release the constriction. For example, ta. If you see ta, your tongue has to move quickly and stop at teeth and release. So, like that, your tongue plays a lot of role in putting a right constrictions in your vocal tract system. That's why people say like that. So yeah. So hope you got some brief introduction about speech. So then let us see how speech look like. So this is a software called Wave Surfer. This is a free software, Wave Surfer. Yeah, you can download just 6 MB or around 8 MB. So actually, this is a software which we can use it for. We can use it for speech recording and basic sampling rate conversion, or any spectrogram, seeing the spectrogram, and observing the quality of the speech signal. So like that. So this is how speech signal look like. Typically, speech signal look like, and usually these ISNR regions are vowels, and you have some small SNR regions. They are also very short. They are consonants actually. These are consonants, and these are vowels. Okay, and you can see this looks like a non-stationary signal. That means obviously the characteristics of signal changing with time, right? It is also obvious because it depends on what you speak. What you speak, your signal will come. So obviously it is non-stationary. Having said that, you see here now, if somebody show this signal and say, is it stationary or non-stationary? So obviously it is stationary, right? So that is why speech is called quasi-stationary. Speech is called quasi-stationary, and this is nothing but your pitch period, the frequency at which these are repeat. This pitch. This is called pitch actually, right? So if you want, you can see in this wave surfer there is something called create plane pitch contour. So that means how your pitch is varying, like that. You can see that. So this is a very preliminary useful software. If you want to record, you can record by switching the red button and stopping at black button actually. So yeah, then let us move on. As I said earlier, speech, the major goal of speech is to make human computer interaction as natural as possible. So that means machine or computer has to understand speech like the way human being understands. But anyway, human being, machine may not have the lot of context knowledge, what context is happening, or any its knowledge are limited actually compared to human being. For most of the speech processing task, human brain is the reference. So but your machine may not understand the speech like human brain. So we'll also during this talk we'll understand what are the limitations of computer versus human brain. So coming to what are the informations present in the speech signal, right? So if I say I am from Hyderabad, okay, if I say I am from Vijayawada, let us say I am from Vijayawada, if I say, right? So what are all information it has? It has information of message and what language I'm using, and what is the gender I am, whether I'm male or female, or what is the age, can you roughly guess my age? And if you know me already, you can also guess who is speaking that, because God has gifted everybody a unique way of speaking, right? So that is why you can also get the speaker identity, and we can also get the emotional state, what I am in. So usually along with our facial expressions and the gestures and other things, we'll also use speech to convey the emotion. So you can also see whether I am speaking, I am telling, let us say I'm from Hyderabad, or I am from Vijayawada, whether I am telling neutrally or angrily or happily. Also you can get, your human brain can understand. And also you can also see whether I have any abnormalities or anybody speech is not proper. That also you can observe. Human brain will do all this, this task, whatever listed in the left side, will be done by human brain effortlessly. Once he is trained, once any person grown up, then he will do all these tasks, in fraction of seconds, without much difficulty. Now the goal is that how can machine will understand these things? How can machine understand these things? So that's why different applications are developed for speech in speech processing. So actually, some of them are you are already using. Actually, that is a good part. So automatic speech recognition and text to speech, these two are very important. As we said, the goal of speech processing is to make human computer as natural as possible, so that communication naturally possible only if these two systems are there. For example, Apple Siri will have only these two systems. What is that? This whatever you speak, Siri will understand. That is called automatic speech recognition. That means speech to text conversion. Your mobile or things will understand your text. So you, whenever you give speech, converting that speech to text is called automatic speech recognition. Then next comes the text to speech. So machine, let us say you asked for weather information. Siri, what is the weather information you asked? Then it will search in the net and see that website says that today is 25 degrees or 30 degrees. So what it says, it will say today weather in Vijayawada is 30 degrees Celsius. Okay, that is called text to speech. Okay, that already we are using a lot of text to speech application actually. So most famous example is actually Google Maps, right? Google Maps. So whenever you, let us say I want to go from Vijayawada to Convener airport, so I will, if I don't know the path, so just I will simply put in the Google Maps, and Google Maps has the text and the voice support application will read the map for you. It will say go straight for 100 meters, take U-turn, go straight for another 500 meters, like that. So who is speaking? Text to speech technology is speaking. Okay. So and also you might be you might be using voice based searching, or even kids are going to Play Store, Google Play Store, and saying that car game, they will touch the microphone and speak. They don't need to type. Even if they don't know correct spelling, they just speak. Or even nowadays they're using OK Google to play some music or some storytelling. These are now happening, and kids are already using actually. Yeah. So these two are the major required application, like automatic speech recognition and text to speech. And then we have we have spoken dialogue systems, or as I said, everybody's speech is different. We can also do speaker recognition from speech. That means input is speech, output is who is that speaker. Okay. And emotion recognition means input is speech and output is whether it is a neutral speech or happy speech or angry speech, etc. And language identification means if input is speech, output is which language it is. So you might have heard, right? When you call to call center or toll free, in some call center things, it will say press 1 for Telugu, press 2 for Hindi, press 3 for English, like that. So why I have to press? I'm speaking. Why can't you understand? So that is why our parents and grandparents, they won't call to call center, because They don't know how to press 1, press 2, etc. So this language identification is very important, especially country like India, where a lot of languages are there. And also we can develop pronunciation evaluation for clinical tools, and we can apply forensic tools based on speaker recognition. And more importantly, we can also use speech coding application in our communication. But anyway, not much machine learning involved here. Yeah, so speech coding is nothing but compact way of representing the speech signal to save our wireless bandwidth, right? So right, wireless channel bandwidth is limited and number of users are more. So we need to incorporate more number of users in the given bandwidth. That is possible if you reduce the bit rate of speech. Just now you have seen the speech signal, right? So you've seen some redundancies there, some kind of periodicity is there. So that can be exploited and reduce the bit rate. Okay, so anyway, it's not much involved in machine learning, so I'm not going to the details of speech coding. So these are the different speech applications. So that is the, all these are applied in different scenarios, like as I said, for better human machine interaction, for information security and authentication, and speech-based smart appliances. So very soon, already I think you might be seen that Alexa device or OK Google device, and similarly you will see even your TV comes with a speech support, or your refrigerator, or even your home appliances will come with the speech input, so you can switch on, switch off them using your speech, right? So and then yeah, so now we are also, I'll come back to these topic slightly later. So and then this no, excuse me, this navigator for disabled people is also can be developed using speech as an input. And also more importantly, we can develop a speech, a lot of speech disorders are there actually nowadays. From last 4-5 years, we are also actively working on speech disorders like cleft palatal problem, or dementia, or dysarthria. More importantly, dysarthria problem and Parkinson problem. So these are all lot of speech production related issues are there, pathological issues are there. So we are also addressing that. So if you can develop technology for that, it can speed up the recovery of the patients. So, and then one important aspect, as I said, I will talk later, that this is the topic that is called speech to speech translation. Speech to speech translation. That means converting one language speech into converting one language speech into other language. For example, if I go to Chennai, I may not know how to speak Tamil. But can technology help? I will speak in Telugu, and can technology convert into Tamil? Is called this speech to speech translation, right? So I think you might have already seen, this our so-called central leaders don't know how to speak our local languages, so they will keep our local translators. So sometimes, they may not translate properly. So even technology also may not be that perfect, but how can technology can do this speech to speech translation? So, and is also very, very important in Indian context, as we have 22 official languages. And if you include Indian English, we have 23 official languages. So this speech to speech is very, very important. So now that Indian government has taken it as a mission problem. So they are investing a lot of money in headed by IIIT Hyderabad, IIT Madras, and few CDACs and few other IITs. And they are developing a lot of resources required in different languages for speech to speech translation. So for this speech to speech translation, what usually happens is, let us say I want to convert Telugu to Tamil. So what I will do, I will take Telugu speech and convert to Telugu text. And there are machine translations. I think you might have also seen in Google. So we can take Telugu text and convert into Tamil text. and the Tamil text can be synthesized using Tamil text to speech, so that Telugu speech will be converted into Tamil, vice versa. So you need speech recognition, machine translation, and text to speech. Already few technologies like with Google and Microsoft, a few technologies are available, but they are they are not perfect. The application what we this IIT Madras and we are all the team of IIIT etc. taken is how can we convert this NPTEL lectures into regional languages, at least major 12 Indian major regional languages. So already there is effort from MHRD and UGC from Swayam projects. They are doing actually manually, they are converting the skilled courses and technical courses from English to regional languages. So, but how can we can develop the technology so that we can speed up that process. We are not saying this technology will solve the problem, but this technology, so these technology will speed up the process. So yeah, so let us see some demo. Actually, I fortunate enough to get one first project on this speech to speech evaluation. So let us see the demo of it actually.
Greetings to one and all. We are from Speech Lab IIIT Hyderabad. Today, we are going to show you a demonstration of a complete end-to-end pipeline of speech-to-speech machine translation for broadcast speeches. The main motto of this project is to convert a Mann Ki Baat audio into other language audio. So, let us consider an audio file which is taken from one of the sessions of Mann Ki Baat. The audio file which we have taken is of 1 minute duration. So let's try to upload it. So in this pipeline, there are three main components. Those are ASR, machine translation, and speech synthesis. The main job of an ASR is to convert a given audio into corresponding text. Machine translation. In machine translation, it takes text as an input and tries to translate to destination language. Whereas in speech synthesis, it takes text as an input and tries to synthesize to corresponding speech. In this platform, we have integrated ASR's API from Google, Microsoft, and CDAC. For the sake of demo, we would be selecting CDAC API. In translation, we have integrated Google's translation API and Microsoft translation API. In TTS, we have integrated Google's TTS API, IIT Madras TTS API, and Microsoft TTS API. So in this demo, we would be selecting IIT Madras. So the source language here is Hindi, and I would like to convert Hindi audio into Telugu audio. So let's start converting. So this platform which we have developed is also robust enough to convert 2 hours audio. But the latency involved in it is around 1 hour roughly. So we have uploaded a 1 minute audio duration file. So it would take nearly 30 seconds to complete the pipeline. So the ASR output is towards left and translated output is towards right. This is the ASR output text. This is the translated text. Let's hear the TTS output.
ప్రియమైన నా దేశ ప్రజలరే, ఇది నా సంతోషం కోసం మన్ కీ బాత్ నా ద్వారా కోహిమా నుంచి కాశ్మీర్ వరకు కన్యాకుమారి వరకు దేశవ్యాప్తంగా పురులందరూ ఒక్కసారి పలకరించే అవకాశం వచ్చింది. హలో మీరంతా మన దేశపు వస్తుత వైవిధ్యం. ఈ విషయాన్ని గుర్తుంచుకోండి. సగిలపడును ప్రతి భారతీయుడు అహంకారంతో నిండిపోతుంది చేసి ఈ వైవిధ్యాన్ని అనుభవించే అవకాశం ఎప్పుడూ ఒకేలా ఉంటుంది. ఉత్తర విక్టరీ అమృతానందంతో ఒక పద్ధతిలో ఆవేదన పుష్పం ఉంది. కొద్ది రోజుల క్రితం నేను ఢిల్లీ చాను చిన్న స్థలంలో మన దేశపు స్వరూపం, సంప్రదాయాలు, ఫుడ్ అండ్ డ్రింక్, భావోద్వేగాల వైవిధ్యాలు కనిపించాయి.
So now let's upload the same audio file. And select Microsoft ASR, translator Microsoft, and speech synthesis also Microsoft. Source languages as it is Hindi, and I would like to convert Hindi audio to English audio. Let's start converting. In this pipeline, the first block is ASR. The ASR tries to convert speech to text, right? And the next block is machine translation. The output of an ASR is fed to machine translation so that it can translate the ASR output text to destination language. Here, the destination language is in English, and the translated output is fed to TTS API. So, the output of translation tries to synthesize and generate TTS outputs here. So roughly it would take 30 seconds as we have given 1 minute audio file. Yes. This is the ASR output, which is generated from Microsoft's API, translation from Microsoft, and synthesis is also from Microsoft. Let's hear the synthesized output.
My dear countrymen, these are my good fortune. Me through that man ki baat. From Kutch to Kohima, Kashmir to Kanyakumari, all citizens across the country. Then there is a chance to greet once. Hello you all, the vastness and diversity of our country. To remember this, to go down to it. Every Indian fills with pride, and there is always an opportunity to experience this diversity, to be overwhelmed, to fill with joy. In a way, there is a flower of inspiration. A few days ago, I have been in Delhi, in Hunar Haat, in a small place, the vastness of our country, culture, traditions, catering, and appeared in the diversity of emotion.
We would like to thank IIT Madras for providing the TTS API, Microsoft Research India Hyderabad team for providing their ASR API, and CDAC Pune for providing their ASR API. Thank you.
So this is the recorded demo. You might have observed that the conversion is not that perfect, but you can understand. So similarly, we have this is my our website asr.iit.ac.in. So here, whatever the speech recognition softwares we develop by collecting data from different sources, we'll host it here. So we have built Hindi ASR, Telugu ASR, and Tamil ASR, and Gujarati ASR, and English ASR, Indian English, and multilingual ASR as well. So we can see the demos of it. And one thing I want to highlight is that we are working on Telugu speech recognition heavily, because we got a project to collect 2000 hours of Telugu data, because Google and Microsoft and these Amazon, these people are using a lot of hours of data for deep learning to give better results. But academia have very less data. So ECE here, this is only 40 hours data. So this 40 hours is much lesser than what Google is using, around 10,000 hours of data. So to scale up the amount of data availability, so we are collecting actually 2,000 hours of Telugu data. That project is going on. We are around already. We have around 300-400 hours we collected using crowdsourcing. So yeah, we will soon put very good Telugu ASR in this website, asr.triple-it.ac.in. So, and also we are working on this something called multilingual thing. So because India is a multilingual society, and this mixing up the languages is very common in Indian language. While speaking, you when you speak Telugu, you in between you will mix up English and other words, because ours is a multilingual society. To handle that problem, and also to handle this data scarcity problem. For example, now I have in few months I will get 2,000 hours of Telugu data. Can I take some 100 hours of Tamil data or Kannada data and use these 2,000 hours also? And can I make a good good speech recognition system for Tamil or Kannada? So that is a question. So that idea is promising, because because even though our vocabulary is different, things are different, but we do share common phonetic space. Common phonetic space means the sounds across the language are same. Some language may have one or two more sounds, but basic sounds are same. So as anyway, for speech recognition, we need to build those phone level models only, which I will discuss in few minutes actually. So this idea of this multilingual is promising. So we developed this multilingual as well. So for example, to see the demo, Padumakkal Mahati Anusar Telidu. Okay, so it has not actually. This is a Tamil word I produced, but it is recognized wrongly. But anyway, this Mahati Anusara is actually a Gujarati word, came in Gujarati script, and Telugu I told it is came in Telugu. Okay, so this is the text speech I have given. Padumakkal Mahati Anusar Telugu. So this one wrongly recognized because amount of data is less. That's fine, but the intention of this showing this demo is that we are using a single recognition system, single speech recognition system. Depending on your speech, it is giving in different scripts automatically. So that is the beauty of this one actually. So we are in the process of commercializing this product, this idea as well. So similarly, if you want to see the Indian English speech recognition, actually this is data released from IIT Madras as a part of challenge. So they are now converting computer science lectures from Indian English to Tamil and Hindi, etc. So they gave computer science NPTEL lectures and some normal English also they give. So it also can understand actually computer science terminology. Computer science, artificial intelligence, data science. I'm giving demo. Computer science, artificial intelligence, data science. I'm giving demo. Okay, so you can see right. So these are we built, and the backend actually is the AI. So backend we are using the neural network based models actually. So let us see more about just to give the a feel for the applications what we are building. So I gave those demos. Let us move on and see what is happening in the background. So now we are giving input and getting the text, etc. So now let us see what happens backend, right? So backend obviously is the artificial intelligence. So it has two steps. One is feature extraction, and then is other one is using the modeling approach. So this is a speech signal nowadays, because of advancement in the deep learning. So especially image processing, people are giving raw images. But even speech, people also started giving the raw speech wave files to the deep learning models, but they are not very popular now. Still, we are using some kind of feature extraction, and then some kind of feature extraction, and using the corresponding machine learning models. So one of the most famous feature is the called malfrequency capsule quotients. So what it does is that, you have seen the speech signal, right? So a time domain signal has a lot of variations actually. So now let us see actually before talking about feature extraction, let us see about, what are the difficulties, why this speech processing took a lot of time actually, because speech recognition started, at least 40 years back. So now only those products are coming. So why it became so, why so much time, why it took so much time to come up with these applications? The reason behind that is the variability present in the speech signal. There are a lot of variations are there. For example, you take the word Vijayawada. Okay, you take the word Vijayawada. If I produce, and if children produce, or if female produces, or if old person produces, so even the word is same, the signal will be completely different. But all human beings, whoever listen that one will understand it as a Vijayawada only. That word they will recognize. Then what is that? What is the common? What are the variabilities? That signal. If you record, if you have 50 odd participant in the talk today, so in the workshop, so all of you record Vijayawada and see. They look entirely different. The signals look entirely different. If you give them, nobody will recognize that, all these 50 files from the same word. But if you play, everybody will perceive the same thing. So there are a lot of variations in the speech signal because of the pitch variations and the speaking style. Somebody speaks fastly, somebody speaks slowly, and the energy level. Somebody speaks loudly, somebody speaks mildly, somebody speaks with low volume, low speaking rate. There are so many variations, right? So that's why we can't use this time domain waveform based features. Actually, they are not robust. Okay. So what is we use is we'll go to the frequency domain and see. There may be some dominant frequencies, or that vocal track features may be common for across the speakers. That's why we are pursuing it as the same word. So we need to little bit reduce the variations and take the useful information from the signal. For that we can't apply Fourier transform for the entire speech signal, right? We can't apply because it won't give any useful information. It will give all the frequencies. It will give, that is of no use actually. So we'll take a small frame by frame, and also we have importantly seen our speech signal is quasi-stationary, and so we can apply Fourier transform properly by taking small frame by frame. You can see here small frame by frame. Usually we may not take frames like this. We'll also take overlapped frames. Okay, that means 0 to 20, 10 to 30, like that. Okay, 0 to 20. The 20 is a tricky thing, and 20 is the actually usual frame size. 20 milliseconds, not seconds. Actually, 20 milliseconds. That means very, very small frame. Okay, where you can assume our signal is stationary and extract the features. That is called malfrequency capsule quotients, or some other features are also there. But we'll process the speech at 20 milliseconds. That how small it is, if you want to understand, the sound ah, you produce ah itself will be around 150 to 200 milliseconds. Within that, you are taking 1/10 of it. Okay, 1/10 of ah sound, you are taking it as a frame. Okay, to extract the useful spectral information or the frequency information. Right. So using those information, you will model speech recognition, speaker recognition, or whatever it is. So that's where the large difference between the human being and machine. So human being can can listen the entire sentence and understand, but unfortunately your machine has to process frame by frame and understand the speech. That is a completely different thing. That is the main issue. Okay, and yeah. So the reason behind this 20 milliseconds is that 20 milliseconds corresponds to usually 2 to 3 pitch cycles. 2 to 3 pitch cycles, right? 2 to 3 pitch cycles. That means your human pitch, usually children will have more pitch, after that females and then males. So it will be around 6 to 9 milliseconds. So this 20 milliseconds correspond to just 2 to 3 pitch cycles, and we assume that our vocal tract system, whatever our resonator is there in speech production, is stationary during that time. Then we'll apply Fourier transform and get the useful information. So simple Fourier transform is not enough. So simple Fourier transform is not enough. So we'll apply Fourier transform and then we'll apply something called capstone analysis. What is this capstone analysis? Capstone analysis means it is a capstone means inverse Fourier transform of logarithm of spectrum. So we have inverse and we have logarithm, and logarithm of Fourier transform is called capstone. Actually, capstone, the word itself is the reverse of spectrum. Actually, first 4 letters of spectrum, if you reverse, you will get capstone. That means capstone is the reverse of spectrum, but not simple spectrum. It's a logarithm of spectrum. So this actually this process, due to lack of time, I'm not going to the details of it actually. So the thing is that this process of this thing will highlight the vocal tract features. Can you please mute yourself? Can please all of you mute yourself? So this process will highlight the vocal tract information actually. Okay, so just to redefine different speech applications, we have something called speaker recognition or speaker verification. That means input is speech, output is whether it is speaker, identifying the speaker or verifying the speaker. Emotion recognition means input is speech and output is which emotion it is. Language identification is input is speech, output is which language it is. Can you please mute yourself, all of you, please? Automatic speech recognition means that is speech to text conversion, and text to speech, TTS means text to speech conversion. Okay, so just to grouping them into different categories. So yeah, coming to grouping up these speech systems, so we can group speaker speaker recognition, language and emotion as one group, and automatic speech recognition and text to speech. These are very important things in speech. So these can be grouped as another group. Actually, these can be considered until unless if you take a text dependent speaker recognition, etc. In general, these systems are simple classification problems. So whatever the model works here will also work here and will also work here. In fact, whatever the model work for, let us say, image classification or any classification model you take, that whatever those take, they will also work here actually. But here, these are not simple classification problems. They are actually require classification and also sequence to sequence mapping. Okay, so that means you are converting speech to text. Okay, we have something. We have applications called automatic speech recognition and text to speech. They require classification as well as sequence to sequence mapping, right? So these actually earlier hidden Markov model used to be famous for these applications, but now recurrent neural networks. networks, recurrent neural networks, because these LSTM sets are now famous because that recurrent neural networks has the concept of memory, so that I can do sequence to sequence mapping. This here we don't need to do any sequential information present in the picture actually. So they are simple classification problems. So whatever the approaches works in speaker, also work for language, also work for emotion. Here also same, whatever the models work for machine translation or speech recognition, text to speech, or video to text conversion, or video to video summary, and all these problems can have a similar modeling approach actually. Earlier in these applications, actually, people used to use Gaussian mixture model. In speech, they used to use Gaussian mixture models as a classic ML model in late 90s. And then slowly they went to GMM, UBM, and then iVector. And then now it is DNN. Okay. Here, as I said earlier, here it is hidden Markov models, and then now it is deep neural network. So I will focus on this application of I will take the example of speaker and emotional language, whichever comes into in the flow, because most of the input may be different, but modeling will be same actually. Okay, the classes may be different, but the approaches will be similar actually. Okay, so we'll see how these machine learning models are evolved over the years in this field actually. So as I said earlier, any of these systems will have this feature extraction and use the machine learning algorithm, and then these are all supervised learning. That's why we'll provide the label also while training, and then we'll build the classifier model. So while testing, by predicting the input, so we'll give the input, and then they will go to the model, and it will predict the what class it is. So for these things, especially in speech, people do use support vector machine, etc. But these Gaussian mixture models are pretty famous actually in the early 2000s and late 90s. So around 98 or sometime, this Steve Reynolds has proposed this. Yeah, those people have proposed this Gaussian mixture models for speaker recognition, then extended to language and emotion recognition as well. So what is this Gaussian mixture model? All of you know, right? Gaussian. Gaussian means you have mean and variance. Mean and variance. You might also remembered, if you have data and it is not fitting into any distribution, it will fit into Gaussian distribution. So, so what here it is that, let us say, for example, I want to do speaker recognition. Okay, around 50 participants are there. I want to recognize all of you using your speech. So what I will do, I need some training data. So I will ask you to speak for about some 10 sentences and give it to me for building the model. So I can use some 8 sentences for training and 2 sentences for testing. So these 8 sentences, okay, 8 sentences may be not very much duration, maybe some 15 seconds, 20 seconds like that. So for every 10 milliseconds, 20 milliseconds, if you take the feature vector with the 10 millisecond shift, okay, so these 20 seconds, whatever the data we have for training, roughly, let us say 20 seconds we have, for these 20 seconds, whatever the data I have, I will get around 2000 feature vectors, because I'm applying window for every 20 millisecond with a shift of 10 milliseconds. So effectively it will be 10 millisecond frame. So I will get around effectively we are getting one frame for every 10 milliseconds. So it will be around 2000 feature vectors. So these 2000 feature vectors are corresponding to one particular speaker. Similarly, for other speakers, I will get around 2000. May not be exact same number, around those numbers. So now the thing is that these 2000 feature vectors, around 2000 feature vectors, I need to model it. What model I should use? I should use some model so that I can recognize the letter whenever I give the test case. So assumption is here. When they propose the Gaussian mixture model, the assumption is this, like this. So fit these 2000 around 2000 feature vectors into some number of Gaussians. For example, here we took 3 Gaussians. So we model, 3 Gaussians, by using this algorithm of expectation maximization. So start with, let us say I have 3 Gaussians. Start with the random means and variances and weights. After that, you take the data points and assign it to the corresponding cluster, right? And then again reconstruct your weight and mean and variance. Okay. Then update again. So you may end up like this. So you, after training, one speaker may look like blue lines and other speaker may look like red lines. So assumption here is that if you feed these features into Gaussian mixture model, then the assumption here is that different speakers mean variance are different. So I will create one Gaussian mixture model for one speaker. So one for blue speaker, for one speaker it may look like blue, another speaker it may look like red. So whenever I get a feature vectors for testing, so if it is a blue speaker, this model will give more probability. If it is a red speaker, this model give a more probability. That is the hypothesis. So here what they found is this idea is interesting and results are coming good. Then what they found is that if I increase the number of speakers, if I want to recognize less number like 10, 50 like that, these are fine. But let us say I want to recognize 1,000 speakers, okay, or 100 speakers. Then obviously I need to consider more Gaussians because some speaker also may be very close to blue speaker. Then these 3 Gaussians may not be enough, right? Obviously we need to have more Gaussians. I think all of you agree with that, right? Having more Gaussians is always better to capture the more variations, right? So now here is the catch. That's why I calculated all those 2000 features, etc. Why? Because if you keep on increase the number of mixtures, performance increases and then start decreases. Performance increases and start decreases. It is because it is not that number of mixtures is wrong. It is because I don't have enough amount of data to train this Gaussian. Let us say I assume 1000 Gaussians. I assumed here only 3 Gaussians, but let us assume I assumed 1000 Gaussians. I have just 2000 feature vectors. Okay, I have just 2000 feature vectors. So if I assume 1000 Gaussians, I may not get samples for most of the Gaussians. So then if I don't get any samples, then their mean, variance and weights will be 0. Then that system won't be trained properly. So if I want to use more Gaussians, I need more data. At the same time, I know 50 of you are there, I want to build your speaker recognition. So all of you give me 1 hour of data. All of you give me 1 hour of data. I will build a very good model for you. But who will give 1 hour? It's not a scaling. 1 hour is very huge. You should take a small amount of data for training and then test it, right? So then the concept of this GMM UBM has come actually, similar to your pre-trained networks, right? You have pre-trained neural networks. Similarly, that concept is already there in GMM. That is called Gaussian mixture model followed by universal background model. What is this universal background model? Let us say I want to recognize 50 of you. Let us assume there may be some workshop going on in computer science department as well. I will go to computer science department and collect those participants' data, small data only. From each one, I will collect some 10 sentences only, but combine all of that. Combine all of that and make 1 hour of data. Make 1 or 2 hours of data from multiple speakers. Okay, and extract the features from 2 hours. I will get so many feature vectors. I will get so many feature vectors. Okay. I will get so many feature vectors, right? So those mean, variance and weights won't be 0. So I can train very big Gaussian. So that Gaussian we are calling it as background model, universal background model. Okay. Then just a second. Yeah. So that is the next concept is you take small amount of data from each speaker only, but you start with the UBM and then you adapt it from the particular speaker data and then and generate the model. That used to work well actually. So we can, that used to be worked well. So from GMM, people went to GMM UBM. Then people went to something called joint factor analysis. Why? Because now UBM has giving some thousand, around 1,000 or whatever the big number of questions I am getting. So I got some super vector using that UBM, that U1 GMM super vector. So, but what they found is that there may be some all the parameters of 1,000 plus parameters are not contributing to the decision making. Can I reduce that one? Can I reduce the can I reduce the uh, yeah, can I reduce that vector into some 200 or 300 dimensional vector, which may help to get the better accuracies. That's where this giant factor analysis applied on UBM vector and produce something called I vector. I means intermediate vector. So I means intermediate vector. That used to be so popular actually in 2010 to up till even 2015, 16. Even now, this I vector is one of the standard model. So then this I vector can be used as a model as well as a feature. So you can extract these I vectors and then train the support vector machine, etc. also. So this I vector used to be very famous. That's how this classical era of modeling like GMM, UBM, I vector, and then so those have come up. Then neural network era has started actually. Don't worry, I'm skipping these slides. Then this neural network era has started. So then people are not comfortable to move to actually this neural network actually. So because over 15 years, 10, 15 years, people have come up to I vector, then suddenly people are asking to apply neural network. They are not willing to move that. So they are trying to say that this GMM is a GMM based thing is a kind of a generative models, and this deep learning is a discriminative model. So better to stick to generative models like that. Some discussion, some resistance, some resistance have come, but now anyway those are all gone. So people are using DNNs. The comparatively, you want to know the difference. What is the difference between this GMM and this DNN is that GMM. Is I am talking it as a generative model. Why? Because, for example, I am taking your data and building the model. I will build only for you. I don't take others' data and build for you. I'll take only your data and build model for you. Take other speaker, model for him, like that. But in neural network, single network has to perform entire task. Let us say I have 50 speakers recognition. Single network has to do all that 50 speakers recognition. Right, there are some architectures which we can build for each speaker, but they are not very popular. But whatever the network you take, one single network has to perform the entire recognition task. So then thing what happened means this is a kind of discriminative learning. That means single network is performing for entire 50 people, so it has to be trained accordingly. So that is the one issue in neural network. And also whenever your training and testing conditions are not same, there is some kind of noise or something is there, those GMMs based ones used to give better performance than neural network. But what these people are saying neural network is that don't worry, you give all sorts of little bit of noisy data also you give, your models may not capture that information, but neural network can capture that information and become robust. So now people have moved to deep neural network. Okay, then people have opted your deep neural network and able to get the performance. Then what is the current architecture? The current architecture is that DNN with attention. DNN with attention. With this concept, I will stop the discussion and then I will show you Python-based demos. I will run few codes and show you that what is the advantage of neural network or whatever we discussed in the beginning of the talk. We told that neural network has more parameters compared to your Gaussian mixture sorry, yeah, whatever the classical machine learning models. So I will, to show that, I will show some Python codes. But this concept of DN, if somebody asks in speech or any classification problems, simple classification, not speech recognition. I am talking about speaker, etc., or language. DNN with attention are the current architectures. Current state of the art approaches is DNN with attention. We propose this DNN with attention for Indian language identification in 2016 in interspeech. Okay. Now some more advancements have come. So here, what is this DN with attention? So that small concept I will touch upon and wind up. You see, this is the one example. What is this? Is that this is the language identification actually. It's not speaker recognition. It is language identification. So I have some 8 languages like French, Japanese, English, etc. So the sentence is given. Testing sentence is, "Hey, thank you for calling me." Okay, thank you for calling me. This is a sentence. Obviously, it is from English. You can see this is the frame level probability. So what happens in deep neural network is that while testing, let us say while testing, this sentence is there. "Hey, thank you for calling me." Obviously, we'll take frame by frame, right? We are not giving the entire sentence. We have entire modeling, testing, everything happen frame by frame, 20 millisecond frame by frame. So I will give 20 millisecond frame and get the decision, 20 millisecond frame and get the decision. Till the end of the test utterance, I will do like that. And then I will see that majority of the time, whatever the class gives, let's say 50, 30, 40% of the frame says that it is English, that is a majority, then I will hypothesize that the test case is from English. What I'm trying to tell is that all frames may not give the right decision. That is obvious. All frames, the 20 millisecond frame is not at all enough to give the right decision all the time. So it will sometimes will confuse. You can see in the beginning it is confused with Japanese or something. All the time it is not the dark. This darkness, let us say, indicates the highest value. You can see the darkness is shifted to different places depending on the frames. What I'm trying to say is that all frames are not giving the right decision, right? Then then the concept of this attention network has come. Then this attention network, what is this attention network? They will give the frame, okay, and they won't go to the output. They will stop at this layer, last hidden layer, and let's say they give first frame, they are calling it as H1, second frame H2, till end of the frames, let's say last frame is T, so this is HT. So I'll create those hidden representations, and I will weight them with output from, there is an attention network, separate network I will train. While the training itself, I will train the network. What it will do is that if this frame is useful, if this is useful, multiply it with the highest value. If it is not useful, multiply with the less value. Based on this attention network weights. So all that will be combined and we will prepare something called context vector. The way you prepare I vector there, you will prepare something called context vector here. This context vector will help us to take the decision at the utterance level, because we have combined all frame level things and prepared something called context vector. Based on the context vector, we will take the decision. That used to work better actually. Okay. So that is, and also nowadays even multi-head attention has come. What is it, multi-head attention? Let us say you have hidden layers. Let us say you have hidden layers, lot of hidden layers, like 120 hidden. Let us say we have 512 hidden layers. Instead of using single attention network, we can use multi-head. Let us say 2 attentions you can use. First 256 one attention, other 256 other attention, like that. So this DNN with attention approaches are right now people are using. So even though 15-20 years of work happened for GMM, UBM, and iVector, now this deep learning architectures are dominating those models actually. Okay. So similarly in speech recognition, people used to use. Yeah, let us skip these things. Where are these? Yeah, in speech recognition also people used to use Gaussian mixture model followed by Markov model. Then the GMM is replaced with DNN. As and when this recurrent neural network has come to replace HMM, that means the memory concept. In earlier when DNN produced, DNN came, there is no concept of memory actually. Initially when their DNNs are becoming popular, but then later this recurrent neural network has come. This LSTMs, etc., where this sequential capturing is possible. That's where these entire HMM is gone. That's why these architectures are also called end-to-end networks. That means end-to-end is neural network. Nowhere you are using classical machine learning. Okay, so now these are dominating in speech recognition actually. Okay, so this is a overview of what is speech processing, how different ML approaches are applied on speech. So let me quickly go to demo. So if you have any questions, you can unmute yourself and speak. So yeah, you have this is a Jupyter notebook where we have codes for GMM as well as DNN. So these actually just for demo purpose, these are not deep neural network or something. It's a small example of speaker recognition. We have some 10 speakers. Each speaker some 1 2 3 4 8 files for training. Okay, and couple of files, 2 files for testing, right? Okay, so yeah, so now these data, and then we'll extract the features and save in this feature folder. Okay, so now let us let us see how GMM and DNN will be trained. So we written the code in IPython Jupyter notebook. The beauty of this one is that we can see the outputs while running here itself in the browser itself. So here we used a package called Librosa package for extracting the MFCC features. You want to extract MFCC features, you can use this one. And for GMM, we used something called sklearn. Sklearn is a package, classical machine learning package. In Python, we can use that one. So in DNNs, we used Keras and Theano background, but nowadays people are using Keras and TensorFlow background because Theano background support is not that much good now. So now this demo is to show, you have data and building the speaker recognition. Let us see if I use GMM, how many parameters I have to fine tune. And if I go to DNN, what are the more parameters I have to fine tune, we can see. Okay, the performance is calculated by using confusion matrix, which I will explain once we run this. So let us say I will start with 4 mixtures. So here in Gaussian mixture model, only parameter which I can vary is or if you want to take 2 parameters, only 2 parameters. One is the number of mixtures, how many Gaussians I can use, and how many times I can do the training. How many iterations I can do. I can do 100 iteration or 50 iteration like that. These 2 parameters only I have, no other parameter. Okay. So let us say I used 4 Gaussians. So let us run all and see. Okay, so we first thing is that we need to give all the required Python packages, and then take the data with the same sampling rate all the cases and give the 20 millisecond frame size, and then extract the features and build your model by using sklearn, right? And then extract those features and test it. Finally, we'll create something called confusion matrix. What is that? We have 10 speakers, right? we'll create a 10 cross 10 matrix. Okay, and ideally this 10 cross 10 matrix should be diagonally all should be 2 to 2. That means we are giving a speaker 1, it should be speaker 1. We are giving speaker 2, it should be speaker 2, like that. But it may not happen like that. You can see this is a confusion matrix. First 2 fine, 2 fine, 2 fine. But speaker 4 not recognized properly. Speaker 4 once recognized properly, 1 is wrongly recognized. Similarly, speaker 6 also not recognized properly, like that. So the accuracy will be sum of these diagonal elements by total number of test cases. So we have 20 test cases. We have seen that we have each speaker 2 test cases. So 20 test cases, and our diagonal elements is 2 plus 2, 4, 6, 7, and this is completely wrongly recognized. 7 plus 2, 9, 9, 9, 1, 10, 12, 14, 16. 16 by 20, we got 80% accuracy. Okay. So now I got 80. I want to change, let me put 8 cautions. Okay, usually we'll put in 2 powers. So let us see whether performance improves or decreases. So ideally it should improve, but if number of features are not enough, it will reduce. Number of cautions is always good, more number of cautions, but we should have enough amount of data to train them actually. Anyway, these are simple GMM. We are not using any UBM here. Okay, so obviously what you observe is that from 4 to 8, there may be improvement. From 8 to 16 or 16 to that means we keep on increase. You can also observe the degradation in the performance. Yeah, you can see 95% accuracy you got from 80. From 4 questions, 80% we have went to 95. That means most of the time we are able to recognize well, right? So now we got 95, there we are still we may go to 100. So let us put number of centers as 16. Okay, you can observe, that now that 95 became 90. Okay, so now if you keep on increase also, it will actually reduces, it won't improve. So I think our GMM training is done. We don't have any other thing to vary to improve. You can observe that, if you keep on increase, already, you may not even get 90, you may go to 80 or something like that. So now our training is done. So we have only few parameters, but we'll see in the DNN actually, pros and cons of DNN also once this simulation is done. you can see it became 75%. It became 75%, right? So now our training is done. Our maximum accuracy is 95 at 8 cautions. That's it. But here in DNN, we may not achieve that kind of performance quickly. But if you keep on increase, there is a chance that, I didn't remember the exact parameters, but I even got 100 for the same data. Here you can see what are the different set of parameters which I highlighted in the beginning of my talk. That here we have so many things. First of all, in neural network, how many number of this, let us say, this neural network is like this. So you have a neural network like this. So how many neurons I should use? How many layers? Can I use 3 hidden layers or 4 hidden layers or 2 hidden layers? As data is less, can I use 2 hidden layers? Then hidden layers, how many neurons I should use, etc. is in our hand. So you can see all these parameters are in our hand. Number of hidden layers in first hidden layer, second hidden layer. Anyway, this input is enough, and this batch size. So whether I should use should be my batch size. As I said, batch size means while training, what subset of each class features I should give to the network. Then similarly, we have here, what sort of loss function and what is the, in what way we can update the weights, etc. There are so many parameters to fine tune actually, right? So for example, you taken some 2 hidden layers and activation function as ReLU. Activation functions also we can vary. And also we can take a dense or dropout. Dense means fully connected. Each neuron is connected to each other. But dropout means we can drop the connections. Some cases dropout works well actually. So only consequence of this neural networks is we need to do a lot of simulations to come up with a better architecture. Suddenly some architecture works, sometimes we may not be able to explain also why it is working. That is also the issue actually. Even the neural network, the beauty is that it will give good accuracies, but the problem is it takes a lot of time for training and fine tuning the parameters and also explainability. Okay, how can we say that this network is why this network is giving the better result, etc. So for example, we took some set of parameters and see restart and run all and see. So here to give the idea, I created a confusion matrix at the frame level, right? Frame level confusion matrix. That means all frames, frame level accuracy may be only 30, 40 only, but utterance level, it will go up actually. That means majority of the frames, if indicate the particular class, that is good enough actually. We can see the frame level access 34 and utterance level access of 70 here. we got. So we can, let us say we got 70, we can increase the number of hidden layers. Okay, let us keep it to 70 and make it 35, and let us say batch size you keep it 20. You can try with different parameters and see the performance actually. Oh, we got the accuracy only 40. So no, actually we need to still optimize the parameters. Okay, let us put 30 and see. So that is how the training, the advantage of GM is that we quickly complete the training and come to the conclusion. Yes, 95 is the maximum we get. But here you keep on try and definitely you will come up with a good accuracy than GMM, and but it takes some more time to see what combination of these parameters work actually. Yeah, you can see now we got 80% accuracy. Okay, so similarly, if you keep on change the parameters, you can there is a chance that you can hit 100 actually. Okay, yeah. With this, I want to stop actually. So if you have any questions, I'm happy to take actually. Somebody asked how to differentiate between vowel and consonants. So yeah, you can use machine learning. That is a simple approach. But if signal level you want to see, vowels usually have long duration, high SNR, and there is some kind of stationarity or periodicity. But consonants usually will have less duration, and even the periodicity is there that looks different in consonants, voiced consonants, like that. So those parameters we can use to differentiate vowel and consonants. Anybody have any questions?
Participants, please respond. You can unmute yourself and ask queries. Participants, you can unmute yourself and ask queries, or you can type in the chat box.
Hello. No questions actually. That means nobody understand anything, or what is? Can anybody? Okay, feedback is already link is given. Huh? Okay. Please share me the feedback so that I can, plan my talk accordingly. Yeah.
Okay, sure.
Organizers. Yeah. Organizers, can we close then if no questions?
Yes, sir.
Yeah. Okay.
Thank you, sir, for your wonderful session. Your session has given a very valuable information, sir, regarding deep learning in speech processing. And a special thanks from all the coordinators and the participants and HOD sir and the principal sir. And I thank all the participants for your very wonderful cooperation. And feedback link is already posted in the chat box. You just fill that and it will be enabled only for the 30 minutes. Thank you so much, sir. And afternoon session will start sharply at 2 o'clock. Thank you so much, sir. And thank you all the participants.
Yeah. Thank you.
Thank you.
Only job for typing. Software